Hi, my name is Dini Nabilah binti Dzul Hamizi, ZID 5652759. Today, I will be talking about understanding the solar system. First, you might wonder what Kepler's laws are. It consists of three laws. The first one, Kepler's first law, or known as law of orbits. All planets move in elliptical orbits with the sun at one focus. Next one, Kepler's second law, or the law of areas. A line that connects a planet to the sun sweeps out equal areas in equal times. So, the planet moves fastest at perihelion, closest to the sun, and slowest at aphelion, which is farthest from the sun. And then next, we have Kepler's third law, or we call it law of periods. The square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. Moving on, let me play the simulation. Thus, the planet moves as the moon's orbits. Upon closer observation, you will notice that the Earth is oscillates slightly as the moon orbits around it. Moving on to where is the center of mass? The first scenario here, the center of mass sits well within the sun, very near its core, which is why the sun hardly seems to move at all. And then we have the second scenario. I shifted the planet's mass by 1.5, where the sun is still vastly more massive, so the center of mass barely moves and remains well within the sun. Next, the third scenario. The star's mass has increased to 1.5, resulting the orbit becomes more elliptical or smaller. Because the star is now relatively heavier, the center of mass has to move closer to the sun in order to balance the planet mass on the other side. Now let's move on. What is the difference between the planet-moon and the sun-planet scenario? Upon comparison, the sun-planet simulation shows the sun did not move. This explains that whenever two objects orbit each other, they both spin around their shared center of mass, the balance point where their masses perfectly balance. So, for the planet-moon, the moon's mass is 1 over 80 of Earth. So when this same force acts, the acceleration of the moon is 80 times larger than Earth. Hence why we noticed earlier that the Earth oscillates slightly. And then in the Sun-Earth, the sun is 330,000 times more massive than Earth. So identical pole give the sun an acceleration 330,000 times smaller. Hence why you cannot see the sun move. So it seems the Earth circles a stationary sun. So the distance between the sun and the Earth is 1 astronomical unit. Based on the screenshot, we can see that there are two boxes, so the distance between each marking is 1 divided by 2 equals to 0.5 AU. Moving on, I will alter the velocity arrow and drag it horizontally, as you can see, further away from the sun. And then, as you can see, it shows that as the planet's distance increases, the value of t squared over r cubed stays relatively consistent, which aligns with Kepler's third law. Well, the values of t squared over r cubed are close but not perfectly identical, which is expected in real-world scenarios due to various factors, such as measurement error. Next, which planets have the fastest orbital velocity? The answer is Mercury, because it is the first and nearest planet to the Sun. It also at an orbital speed of about 47.4 km per second, which is a period of about 88 Earth days. Second question, which planet has the slowest orbital velocity? The answer is Neptune, which is a period of 59,800 Earth days at 5.4 km per second. What is the reason behind it? Kepler's third law explains that a planet's orbital period increases as its distance from the sun increases. The planet closest to the sun, like Mercury, experience a stronger gravitational pull, causing them to orbit faster. The planet, like Neptune, experiences a weaker gravitational pull from the sun because it is farther away. As the distance grows, the gravitational force decreases, causing the planet to move more slowly in its orbit. Last but not least, what did I learn in this experiment? As someone who is new to physics, I found this simulation very helpful in deepening my understanding of the universe. I discovered how Kepler's third law affects planetary motion, particularly the relationship between a planet's distance and orbital period. Additionally, I discovered how orbital velocity is influenced by distance. That's all from me. Thank you.